Hey everybody, Dr. A here, and in this video we're going to be providing some background information as it pertains to real moving loads along a beam. So let's go ahead and get started. We're going to get started first with a real single moving point load, okay? So here what we have is when a single, that's one, real moving point load moves across a beam, what we do is we multiply the influence line ordinates by the magnitude of that point load to compute the magnitude of the desired effect for a particular location of the load, okay? So maybe pause the video and write that down. That does sound a little confusing. Let's draw an illustration to show what we're talking about. Let's say that we have a simply supported beam here. Let's say that, we got a roller here and a pin here. And, let's say that this is, point A and point B, okay? And then we're going to put, the coordinate X there. And then, of course, let's say that this total length is L, all right? So what does the influence line for AY look like? What's the shape of the influence line for AY? Well, we remember from our previous knowledge that if we want to sketch the influence line for AY, it's going to look something like this. This is, AY, this is X, and we're going to get an influence line that's shaped kind of like that, okay? And then, of course, this is L right here. And then, this point right here is 1. And we've seen this before. We've done this a brute force method. We've done this with influence functions, okay? So if we have a real moving load with, say, a magnitude F. So let's say that, we have this real moving load with a magnitude F, and we want to know what the real reaction AY is as F moves across this beam. What we do is we multiply that magnitude F by the influence ordinate at a particular spot that we're interested in. So let's write this down. So what we would do is we multiply F by the ordinate. Ordinate's like the Y value, right? It's like this 1 is an ordinate right here. The ordinate of interest. So for example, at X equals 0, then AY equals 1 times F, which is just F. That makes sense, okay? What if we were interested in X equals L over 2, okay? Then what we're interested in is if X equals L over 2, then we multiply it by this ordinate. That should be 0.5. So if I were to sketch that here, this is just a straight line. So if we were at L over 2, of course, this is 0.5. We already know that. So we could say at X equals L over 2, AY is 0.5 times F, which of course is just 0.5 F, okay? So it's pretty simple, and again, I made this illustration based on the influence line for AY, which is a pretty simple situation, okay? So basically this just says, hey, if you got a real moving load with magnitude F, multiply it by the Y value from the influence line, and that'll get you what AY is when F is at a particular location. So what's AY when X equals L? When X is all the way out here, AY is just 0. Makes sense, okay? And we've seen this concept before, especially when we talked about trusses, okay? Now, what about if we have multiple real moving loads in series? Well, if we have multiple real moving loads in series, what we do is pretty much the same thing. We multiply the ordinates of the load by the load magnitudes and add them together to get the desired effect. And And then we say the worst case or largest magnitude of a particular effect is generally determined when the loads are in the vicinity of the peaks on the influence line, okay? So let's do another example, okay? Let's say that we have that same beam, okay? So let's say that we've got, the same simply supported beam. Here's the roller at A, here's the pin at B, and here's our direction variable here. And I'm just going to go ahead and resketch our influence line. So here's AY, here's X, total length is L. So the influence line again, let me draw that with a straight edge. This line looks like this, and here's 1, and here's L. Okay, same thing that we saw before, except this time, let's say that we have these two moving loads, okay, that are in series. Let's say that we've got them like this, and this is maybe F1 and F2, and let's say that there's a distance in between them, okay? So let's put this distance at D right here. All right, so the question becomes, how do we reconcile this? Well, we slide these loads along this influence line with that controlled distance D in between them, okay? And then what we do is we multiply F1 by this influence ordinate, and then we multiply F2 by this influence ordinate, and we add them together, okay? So what we can do is we could say, for example, we could say AY is equal to F1 multiplied by influence ordinate 1 plus F2 is multiplied by influence ordinate 2, and you see we add them together. Now, look at that next sentence here in my description. The worst case or largest magnitude of an effect is generally determined when the loads are in the vicinity of the peaks of the influence line. So if I were to maximize AY, right, if I wanted to get a maximum value of AY, where would that occur? Well, that would occur when F2 and F1 are pretty close to that peak right there, that high point of 1. All right, now this might require some trial and error because, depending on exactly where the peak is and what the magnitudes of F1 and F2 and D are, you might have to do a couple of trials to figure out what will actually maximize that load effect. So we'll put a note here. We're going to say a trial/error approach may be taken depending on the magnitudes of F1, F2, and D, and the shape of the influence line, the IL, okay? And again, we'll see another video with some examples of this, but this is the idea behind it, okay? You might also have to do a little bit of math, a little bit of algebra to get what these influence ordinates are. All right, and then the third situation here is, what if you have a moving, uniformly distributed load? Well, in that case, what you do is you multiply the area under the influence line by the magnitude of the distributed load to get the particular effect. So similar to before, let's say that we have this beam here, and here's the roller, here's the pin, there's X, and let's say that we've got this. Let's change colors here. Use purple. Let's say we got this moving distributed load. And the length over which it's distributed is not really what matters. What matters is the area beneath the influence line. That's what really matters, okay? So let's say this is point A. And again, let's sketch this influence line. Hopefully we're all really comfortable with sketching influence lines for reactions now because we've done it so many times. But this is, you know, AY. This is X. And you know that influence line is going to look like this for AY. This is L, this is 1. Okay, so if you want to maximize AY in this case, what you do is you multiply the area beneath the influence line by W, okay? So let's write that down. We can say, AY max is equal to the magnitude of the distributed load W times area beneath influence line. So in this case, AY max is equal to W times 1/2 times 1 times L. Okay, and again, this is a simple illustration. Depending on your particular beam and the influence line shape and the effect, this could get a little bit more geometrically challenging, but this is the concept behind it, okay? So hopefully this background information was helpful to you. We're gonna have a couple of video examples illustrating these concepts, so be on the lookout for that, and please don't forget to hit like and subscribe. Thanks for watching.